Engineers, how's it going? Old Aaliyah, Landon, Ben are here. Outstanding. I am sharing a screen and let's get after it. What questions do you have for me? Is this format working for you? Let's see here. I'll make you guys nice and big so I can see your faces. Big picture, just giving you a chance to kind of think a little bit. As I mentioned, I said this before, but I'm just interested in making sure you see the big picture. With respect to statics, we want stuff not to move. And there's sort of two types of motion. One of them is what a mathematician would call translation, which is, oh, it moved up, it moved left, it moved down. We don't want stuff moving. We don't want bridges moving. The second thing we don't want is stuff rotating. So the two types of motion are translations and rotations, if you will. So what we're studying right now is the rotational component of that, what engineers call not torque, but moment. As I said, there's a subtle distinction between those two, but we're just talking about moment. And really what we're trying to do ultimately, which you may have noticed in the week and a half we've been looking at this, is resultance. In other words, there's a whole bunch of forces on something, poke, 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 forces pushing on it everywhere. And we're just interested in understanding what's the result of that. Which way is that going to make this thing want to go? Because if we understand the result, then we can say, oh, no, now I'll attach this cable over here and then it won't be able to move like all those forces are trying to get it to move. And effectively, we're really to think about it like this is if we said, hey, there's 8 forces on this and the result is my pen right here. Then all I have to do is say, well, awesome. If it wants to go that angle at 640 kips, what's a kip? I'm asking that of you. Did you see that in the assignments yet? Kip. What's a kip?
I think isn't 1,000 pounds or something?
Yeah, kilopound. So it's
I was like, I saw it in the answers. I had to look it up.
yeah. It just jumped into my mind. But yeah, and you'll almost always, if you're an engineer in America, you'll almost always be calculating things in kips because you never have forces like 80 pounds. Like that's nothing. You have thousands of pounds. So it's really kp, kilopound, but you can't really say kp. So kip, kilopound. The I is maybe the I in kilo, but kips. And so if this is going off, once the result of this is going this direction at 64 kips, then I'm just going to have to turn around and put a cable on the other side that's strong enough to pull back at 64 kips. And so in that way, the forces will all be balanced. I'll have this wire pulling in the other direction. So I need to know the resultant direction it's pulling so that I can attach the cable in the right location, 180 degrees off. Again, this course will never be addressing, what do you do to stop this from moving? But you can see it's not a very large step to do so. And of course, if I put that force on this system and I'm pushing on it, then it also might want to rotate. And so I'm going to have to do something to figure that as well. So I need to figure out how much is this thing rotating so that I can make sure I attach it in such a way that that doesn't happen. Does that concept make sense? And so we're studying moments now as kind of our second set of problems. And you're going to want to stare now really carefully at the note sheet that I gave because I'm going to show you something a little harder. But to introduce that, let me just show you the logic of it really quickly because again, I'm interested in teaching how to think in this course. So similar to the bike the other day, Chapter 4, moments. And please interrupt. Don't raise your hand. Just start talking. Just interrupt me immediately. So with the case of the bike the other day, we basically had a force that was kind of up in the air. And what I'm going to do is give you some conceptual understanding of what a cross product is. And have you seen, because Ben brought this up the other day and I was sort of surprised to hear him say it. Where have you guys seen formally cross product someplace, or Ben, did you just know that because you studied into it? Maybe you could answer first, Ben. Did you see that in physics?
Yeah, that was in physics. Okay. When we talked about torque. We studied cross product.
Sweet. Okay. Got it. And again, I'm going to teach this stuff kind of from scratch as though you've never seen it before. But what I want to do is motivate how a cross product really works. And so in the end, for the bike the other day, for instance, we had a force, and I'm just going to make up a brand new problem just to give you a chance to think about this a little bit. And I'm also, I think I'm going to send the force off in some other direction just because so it doesn't look exactly like the same problem. So let's say here's the force, and we'll say it's 9 kips. So this isn't a bike anymore because it's 9,000 pounds of force, and so that's not going to happen on a bike. And we'll also say that that angle right there, that looks almost 90, we'll say it's 82 degrees. And it's acting on, well, what again we call a particle. Now, what is that particle? Well, it's a bike and a biker reduced to a point in space. So that'd be their center of mass. And that was causing rotation because their wheel was on the ground sort of back over here. And so this is point O. And so what we're trying to calculate here is the moment around point O. O for origin or something like that. I want to calculate the moment around point O. So can you picture that as the center of mass of the biker, and that's their back wheel touching the ground back there, for instance, just as a real application for this. And then I'm going to add to this a couple of things, like how far is that off the ground? We'll say that's 2 meters off the ground, and we'll say this is 1.1 meters. We don't want it to be 1. That's a little too boring. And again, you already know this. So let's figure out this force here. So what is that force vertically, we say? Well, vertically is straight up and down. So that would be here. That would be the force vertical. And of course, let's see, what would that be? Sine or cosine? It's going to be 9 kips times, well, let's see, this is the hypotenuse. And the angle is 82. So in this case, that 82 is adjacent to it. So it's cosine in this case. Cosine, am I right? Cosine of 82. Again, it depends where the angle is located. Speaking of locating, I'm now locating my calculator, and because I'm teaching calculus, I am converting it back to degree mode. I'm making this problem up on the fly, so I don't know the answers to this stuff. 9 times the cosine of 82. I got 1.25. Does it make sense it would be that small? Would it be really small? Sense making, constantly sense making. Should be doing that when you're doing all your problems. Does that make sense? It would be a small number, like closer to something small as opposed to like closer to 9. You should say yes, because it's not pushing anywhere near the same direction. Would you agree this is the force vertical? I'm sorry, that's the force horizontal. And notice it's pointing virtually in the same direction. It's only 8 degrees off. And so force horizontal should actually be pretty close to 9. But its component vertical is pointing in a totally different direction, so it's way smaller. So that means I didn't screw up. Cosine was the right one. You see what I'm saying? Like that'd be easy to screw up. And in my case, I'm getting in a little too much of a hurry, so it wouldn't have surprised me if I screwed up. So that'll be 9 times the sine of 82 degrees. And so force horizontal is approximately 9. Sine of 82 is, oh yeah, 8.91. So I'm highlighting for myself that all this time, blah, 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 and I've got these 2 answers, and that's what I really need. And so given that moment or torque is force times perpendicular distance, can you see what it takes now to get the answer to this question? And again, I'm going to obey the convention that rotation in this direction is negative, whereas rotation in that direction is positive. That's what we called it in Math 112. Counterclockwise rotation is positive, clockwise is negative. So I'm just going to do this with positives and negatives. So what is my moment around O? Well, it's a force times the distance. So let's see, what am I multiplying force of V by? That's its force. Notice the force was in pounds. I didn't have to convert it to newtons. What is that multiplied by for a distance?
Would it be 1.1?
Yeah, again, the concept that it can move. Does it make sense that in order to get the perpendicular distance to O, I sort of have to think of force V as down here, which means the 1.1 is its distance. Do you see that as being perpendicular? Are you okay with the fact that I could move that vector? The action along which it's acting is that dotted line. And so its distance perpendicular is 1.1. And that is a negative rotation. I can see now that I put it down there, it's causing rotation, if you will, in this direction around 0.0. And so we call that negative. So I'm going to call it negative. And then we have the other force of H, which is, again, I haven't decided whether this is positive or negative yet, 8.91. Do you see that as, well, there's its perpendicular distance right there. And that's 2. So because of where it's located right here, 2, again, do you see that as rotating in this direction? So, oh, they're working together. That's also a negative, I now know. So again, I'm hoping you say, yeah, I'm getting that now. We did a little bit of that. I did that in my assignment. I get that now. So they're both negative. But I want you to step back for 1 second and actually think about what you just did right here. And this is why a cross product works. A cross product is a mnemonic device, a technique that does this automatically for you without you having to think. Because remember, we got to go 3D with this. We have to have the same exact thing happen, but not in a flat plane, but in 3 dimensions. And we're not going to be able to see this very well in 3 dimensions. But I want you to stop and think about what you just did. This 1.25 was the force vertical. What was 1.1? 1.1 is really the distance, the x distance. Isn't that horizontal? Like it was the x distance. So it was like the y force, and maybe I'll even write it that way. It was the y force times the x distance. That's going to happen every single time. The y force is not going to have a y distance because it's got to be perpendicular. So if the force in y is vertical, then the horizontal is perpendicular to that. That's going to have to switch to x. Do you see what I'm saying? Logic in that? And then notice what happens with the other one. The 8.91 was actually the force horizontal, or the force in x, which would be perpendicular to the distance in y. And so the cross product just exploits that fact that, hey, it's always a force in one direction times the distance in another direction every single time. Now, if you can appreciate this, when we go to 3D, that's going to get rather complicated. So that's effectively what a cross product is doing. When you took physics, did you write that out as a, and I want to do that now. So let's see, force cross distance. Don't write this down because I'm going to write this down based on logic here, not based on, and I'll show you the formula for this in just a second, but there's something called a determinant. Were you taught it that way in physics? Does that ring a bell, determinant, or was it not taught that way? I'll launch into the logic of this because, as I said, this is a mnemonic device. It's a mental trick that allows you to kind of get this right. And so I think I'm going to write it the other way. I'm going to write it a little closer to the note sheet that I'm going to give you and kind of put the distance first and the force second. And that is cross product, not the multiplication sign. And you're actually multiplying vectors here in a sense. So the way that you could write this is in the first row, you write your distances. You write, and it's kind of X's and Y's. In other words, right, you write your distance in X, which is 1.1, and you write your distance in Y, which is 2. So these are your distances, and these are your forces. And this is the X, and this is the Y every time. So your forces, your force in X was going right 88.91. Your force in Y, however, was going down negatively. Do you agree with that? So it was negative 1.25. And you don't always get the distances do not always get to be positive here, because they can be negative too, can't they? Like not just the forces, but also the distances. And really the distance has to do with how far away is the force, how far is the way of, how far away is the force from that point O? Would you agree in normal notation, it would be, hey, I go right 1.1, which is actually positive 1.1, and then I go up 2. That's a positive 2. So in this case, they're both positive, but they're not always both positive. It's basically how far away, this is sort of like the distance from the point of rotation to the vector, or I should say to the force vector. And if you haven't seen this before, and I'm sure you have in physics, I'm going to put a little vector symbol over it. How far away is it? And then 8.91 is the force vector of X, and negative 1.25 is the force vector in Y. Have you seen this before? A determinant? Yes or no, I don't care, but have you seen this? So this symbol right here means take the determinant. And all that is, as I said, a mnemonic device. It's a way mathematicians have come up with, because now that those numbers are all written correctly in the box, what you do is you start with the upper left and you multiply it by the lower right. You say, I'm going to take 1.1 and multiply it by negative 1.25. That's the first move. And then you always subtract the other one, second. 2 times 8.91. Do you see that that reproduced the same math that we did above, just using logic? Above, we used logic. We just looked at the pictures and said, I see the force and I see the distance, and I can tell in my mind's eye that that's rotating clockwise, and I call that negative. Like I had to think. Do you see what I'm saying? And for me personally, I would prefer to think. Like I like to make sense of stuff. Don't show me these complicated mnemonic devices that I don't really understand, and maybe they produce the right answer, but it's like I want to see the logic of them. Down here, the logic is lost, but notice you get the same answer. But you got to be careful about the signs, because you got to get the answer to the signs correct and so forth. But that's the logic of what a determinant is. The cool thing about a determinant is, does it make sense you can memorize that? So you like multiply diagonally and multiply diagonally and you subtract them. That's what you do to take a determinant. Do you see how that accomplishes the fact that we took the X distance times the Y force and the Y distance times the X force? So mathematicians just said, hey, if you just multiply this in a cross pattern, you know, was that explained to you clearly enough that you went, oh, okay, that makes sense. I understand where that comes from. What I want to do now, though, is take that 3D where we're not going to be able to do this logically anymore. It's very hard anyway. And what I would like to do, are you looking at my note sheet? Pull that up. get that in front of you because I don't want to share the screen to get it up in front of you. But note number 5, you just did really note number 4. Note number 4 says moment of a force about a point O is force times distance, and D is perpendicular distance from O to the force F. We just saw that happening. It's the perpendicular distance from the point O to that force itself. That's what that distance is. It just isn't any old distance. It isn't the distance from O up to that center of mass point. It's got to be perpendicular. Well, now we're going to jump to the one below it. Notice it says moment of O is R cross F, and there's this huge 3x3 matrix up there. Well, our matrix that we just did is 2x2, but if we're going to do this in 3 dimensions, it's going to have to be 3x3. And then notice it describes right after that big matrix what it means to take its determinant. And I will show you this at some point, but I'm assuming you're looking at your notes. But it's real confusing looking. It's like RYFZ minus RZFY times I minus RXFZ minus RZFXJ. And so it's confusing looking. And we'll do this in a second and it'll make sense to you. But the only thing I want to show you before we kind of launch into this too completely is, this is a picture in your book. I don't think I wrote down what page it's on. Let me see if I can find it in here. So we have before us here the exact same picture I just gave you, except for now we got a third dimension to it. Do you see that? Again, please chime in. This is too much of a monologue. You guys aren't talking enough. So here's the point around which I'm interested in rotating. And this R here for radius is how far away is the force that's actually causing the rotation. So I just want to highlight a couple of things. So there's the R. That's kind of R is the distance. And I think, as I said, in 3D, maybe it makes sense to call it R instead of D because it's kind of like a radius. And then here's the actual force itself. That's capital F. That's the force itself. And so I don't know about you, but isn't that kind of hard to picture? Like, what direction is F actually aiming? Is it toward me? Is it away from me? Do you see what I'm saying? Like, you can only draw a 2-dimensional picture of something in 3D. Now, there are some clues about this. Can you actually see it? Because again, I want to just give you a shot at understanding, at least spend 10 minutes here, understanding the logic of this. So where is R actually pointing? Is R pointing toward us, away from us? Are the components of R, and would you agree that R is, let's go back to green, stay all the same color. R is a vector, Rx, Ry, and Rz. In other words, those are the distances. A second ago, our distances were distance in y. In other words, Ry was 2 and Rx was 1.1. Right now we just have a third one, Rz. Well, notice the arrow from O to R. You see that there's some other boxes there to show you where those things are, and they actually label them for you, right? Do you see that? Like there's Rx. So you start off from 0 and you go positively in the X direction, and then positively in the Y direction. That's Ry. Notice it's labeled over here though instead. And then vertically Rz, which is labeled over there. So it's actually positive X, positive Y, positive Z. And now you know what direction R is actually pointing. Do you see it now? Okay, so those are my distances. I have 3 of them this time that locate the point, not 2. Then there's my force. My force, which is also an X component, a Y component, and a Z component. And notice those are a little easier to see. So from Do you agree that that's the point, right? That's the center of mass, the one that I just drew in. So what direction is that force vector going? Well, notice I'm told here that force of X, notice that's parallel to the X-axis. That's very important that you see that. And force Y is going to the right, parallel to the Y-axis, and then force Z is going up. And so what we're interested in here is the moment of a force around a point in 3D, and that point specifically is point O in this picture. So we have the force, and it's trying to cause that to rotate. Do you see that? Now let's see if we can, this picture, watch the cross product start to happen here. I just want you to see the same thing that you just saw happen in 2 dimensions where it was a little easier to see. I just want you to at least have a shot at seeing this happen in 3 dimensions. So rotated around point O. So let's start with, let's just not start in any particular order. Let's just go X's first. And so let's see, I'm going to switch to blue. This force X right here. How far is that away from? How far is that away from O? There's kind of more than one answer to that. Again, you got to picture that box that's being drawn there. Notice it's parallel to this plane right here. That's where RY, that's where f of x is actually pointing. So f of x is in this plane right here.
Is that RY, RZ?
Yeah. Do you see? And again, you don't have to get this. Like I'll show you how to use the mnemonic device, and you'll get it. I just want to give you a shot at understanding it. Remember, force of x is acting along that line right there. You agree with that? It can sort of be thought of as being anywhere on that line. Well, would you agree this is one of its perpendicular distances right here? How long is that? What length name is that given? You see it down here. It's r in the y direction. So it's force of x. That's its force times a distance of y. Force x times distance y. Isn't that what we just saw just a minute ago? Same thing, right? Is that its only distance? What else is there?
RZ, like Evolt said.
RZ as well. Why? Like, where do you see it? Like I just drew in force of x here times perpendicular distance to the z-axis. But where do you see, like you might think, I don't see it. Where is it? Well, isn't it above the y-axis right there? So you also have force of x being multiplied by distance z. Both of those are causing rotations around point O. Now, perhaps you can visually see whether that's positive or negative, but you also agree in this world, it's really hard to tell what positive and negative rotation is. What does that even mean? We'll talk about that a little bit later. Stare at this for a second. So this first one, this force of X times R of Y, would you agree that's causing rotation around the Z axis? If you think of force X being right here, and it's a distance of Ry away from that, then isn't that causing kind of flattish rotation around the Z axis? Can you see that? I'll try to draw it a little better. So force of X is causing rotation around Z. What is force of X times R of Z causing rotation around? Again, this is RZ. So can you see that force of X being this distance away from Y, isn't that causing rotation around the Y axis? You agree with that? So this is actually causing rotation around the Y axis. But you see that in one sense, I could probably stop right now. If I continue to write on this, it's going to end up so messed up, you're not going to be able to see anything. But do you see what's happening? We're always taking a force in one dimension and multiplying it by a distance in another dimension. It's never force of X times distance of X. Why is it never force of X times distance of X? What do you notice about those two directions? There's force of X, there's distance of X. They're never perpendicular to each other. Do you see what I mean? That's why, so basically force of X is going to get multiplied by a radius of Y and a radius of Z. If that's true, I'm just thinking out loud here, wouldn't it be true then that if I move to force of Y, what radiuses is it going to be multiplied by? Well, it's parallel to Y, so it's never going to be multiplied by the radius of Y, but it will be multiplied by the radius of X and the radius of Z. Like, aren't those the ones missing? See, that's my point, is the pattern is going to stay the same. Let's see if we can visualize those like actually happening. I just wrote those down by pattern. And notice I haven't put anything about signs, like is it positive, negative? I mean, I'm a little bit lost with that. But let's just try to visualize it. So let's see, force of Y. Force of Y is right over here. I'm going to darken that in. Force of Y is going this way, which remember means it's acting along this axis, kind of goes, that's its line of action. So if I move it back to this beginning over by B over there, do you see that it's that far away from the Z axis? Do you agree that that length, which I can see right below it, is actually Rx? Do you agree that because that arrow is aiming to the right, it's actually causing rotation around the Z axis in the opposite direction of the orange one? Do you agree with that? They're like fighting against each other. So by simple pattern, force of Y times radius of X, force of Y times, hey, that was this one right here. And from the picture, I can actually see that that's causing rotation around the Z axis. Again, if your brain's hurting, you don't have to know this. I'm going to show you the shortcut. I'm going to show you how to use it in just a minute. But this is why cross products are invented, because I'm really going to need this in 3D because my head is spinning. I can't really make sense of this. What's the force of Y times the R of Z? Do you see that one? I have to work at this. I've taught this 5 times and I still have to stare at it and think, wait, why is that? I'm staring at it right now and I still kind of don't see it yet. I'm looking at the force of y here and saying, what does r of z have to do with it? What about that distance? What is that? That's here. It's here. Ah, I think I see it now. It's in that location right there. Again, notice the labels are kind of confusing. That length is actually r of z, the same as this length over here. And so those are perpendicular. And so do you see that that's actually causing rotation around the x-axis? You see that? What pattern do you see in all of this? What axis did force of x and r of distance y rotate around? Z. What axis did force of x and distance z rotate around? Y. What's the pattern?
It's the axis. It's not involved in the.
Exactly. It's whatever's missing.
Yeah, whatever.
Force of y times r of z. What axis is it going to go around? Well, we got y and z covered. It must be x. Now I can see that in this picture, but you see, mathematicians just try to look at this stuff and try to come up with a way to take advantage of that. Armed with that, I actually think I know all the last ones without even doing them. Don't you? I think I can write the whole last list down without even doing anything. So the last one then would be, let's see, I've done force of x, force of y. So I need force of z. I'm going to have two of those. And force of z will not be multiplied by itself. So it'll have a radius of y and it'll have a radius of x. And since that first example there has a z and a y, isn't this going to rotate around the one that's missing, x, and this one's going to rotate around the one that's missing, y? And so if I could just add all those up together, so there's actually 1, 2, 3, 4, 5, 6. In the last problem, when 2 dimensions, there was only 2 moments. This one's got 6. And if I add all those up, I'll get the right answer. But you understand, some are wanting to rotate clockwise and some counterclockwise, and we got 3 different dimensions. And so I'm very worried about the signs, aren't you? Like one is positive, one is negative. It's like, oh my gosh, I can't just add them as numbers because if they're all positive, then I would add them all together. But if some are negative, then they're actually going to be subtracting. And so this is very confusing. Now, can you look at your note sheet, which I'll switch to in just a minute, and can you stare at the fact and see how the signs are all taken care of there? There's a bunch of signs mixed into that. How come it says RYFZ minus RZFY, and then it's multiplied by I? Why does it say times I? Well, stare at my sheet over here for a second. Stare at my notes. I haven't went away from it yet. Rotation in X, rotation in X. Which ones are taking care of the rotation in X? It's force of Y, radius of Z, force of Z, radius of Y. It's all the non-X terms that are basically giving you the rotation around the X axis. So if I just multiply those and add them together, just like the determinant we did just a minute ago, then that'll tell me everything that's happening to X. Isn't that what I does? I is kind of the term for what's happening around the X axis. And then if you switch to the Y axis, don't you see the same pattern? Where does the total rotation around the Y axis come from? It comes from force of X, distance of Z, force of Z, distance of X. Now, Now let's actually kind of do this. Let's go carry this out. And Landon, you posted something in the chat. Why don't you elaborate on what you're, don't, spend 20 minutes, but why are you, what is that you're pointing out?
Oh, it's the determinant shortcut I used a lot in linear algebra, where you just go, draw the diagonal lines where the ones going to the bottom right are positive and ones that going to the bottom left are negative.
That's exactly right. And that's exactly where we're going to go right now. In other words, everything I just showed you is very confusing, and it's neat to be able to conceptualize where the cross product comes from. But we got to actually, be able to pull it off and not screw up all the signs. And so what I want to do is take the two-dimensional cross product that we just did and then jump to 3, which I think is what Landon is getting to. And don't feel shy about chiming in about that if there's something you want to say. So I started off the class showing you this diagram right here, and this is one of the questions out of your book. And incidentally, on a side note, see how it says asterisk 432? That means that problem, the answer isn't in the back of the book. So primarily the examples I'm using are the ones that don't have the answer in the back, just because I can't really assign those to you because I want you to be able to check your work. But let's see if we can pull this off. So this is asking, how much is this force? Notice there's force F down there. And thank God they broke it up to us into its X, Y, and Z components. Otherwise, we'd have had to do that ourselves. Do you agree with that? We need the X, Y, and Z components. And fortunately, they just told us that. And with 3D, they kind of have to. Although, and you did in your previous chapter 2 assignment, you did it yourself when they gave you coordinate direction angles and azimuth and zenith and so forth. It's like, wow, those are really hard to see. Thank God they gave us those. And notice there's 2 are positive and 1 is negative. So can you take a second and picture which way that force is going? Let's see, positive X. I'm just going to draw on this and erase it. But so from here, it's positive X. There's the positive X direction. Positive Y. And then negative Z. So it must be positive X. I went too far. And let's go back and get it kind of accurate now. Because again, that picture does no good whatsoever. You cannot tell where that force is pointing by looking at this picture. But they're basically saying positive X, positive Y, negative Z. Oh, okay. I see where it's pointing now. So, okay, at least I understand that conceptually. Now, I don't really have to understand it conceptually because they told me the numbers and they told me positives and negatives. Now, for radius, we've got to get from here, which is the point of rotation, to here. That's how far away, this is just like what I started the class with. That's how far away our force is from the point of rotation. Exactly what we did at the start of class. It's just that the start of class was 2D. How far is that? How far is it in X? From that drawing that I just did, what is the X? How far in X are you going? So would you agree that, I'm just going to not draw on it, you go 0.5 in the X direction, and then you go 0.4 in the Y direction, and then down 3 in the Z direction, and then another 0.3 in the Y direction. Can you see that? So how much total did I go in the X direction?
0.5.
0.5. Is it positive or negative? Does that matter?
Yeah, it's positive.
It matters a lot. And because we went that way and the X is over here, that's a positive X. So positive 0.5. What about Y? How far did we go in the Y? Blurt it out. 0.4 and then 0.3. So 0.7. You agree with that? And again, we went toward Y, so that's positive. What about Z? How far did we go in the Z direction? We only did one thing in the Z direction, that was right here. Again, it says 0.3, but we went down 0.3, right? So that's actually negative 0.3. So from that confusing drawing that I just gave, does it make sense we've got to multiply? Again, we're going to do this in a systematic way, but we got to take 600 here and multiply by which of these? 600 is what?
The x. So we multiply it by the y and the z.
Exactly. It's the x, and so we're going to multiply by the y and the z. This 800 is the y, so we're going to multiply it by the 5 for x and the 3 for z. And then this 500 is a z, so we're going to multiply it by the 5 and the 7. But it's like, that's a lot to keep track of. So here's the cool mnemonic device that Landon was actually alluding to. So what you do, according to my note sheet, you say, if you would like to know the moment around point O, and you might notice in my note sheet that there's a little vector symbol above that. Let's forget about that for a second and let's move on. It says all you got to do is take R cross F. What does R cross F mean? It means write yourself out a matrix. Put an I here, a J here, and a K here. Remember, those are just symbols that help you remember what's X, what's Y, what's Z. Write that out. No notes about that. And then the next row is RX, RY, RZ. So 0.5, 0.7, negative 0.3. And the next row is all the forces. Force of X, force of Y, force of Z. Force of X, 600. Force of Y, 800. Force of Z, negative 500. I haven't paid any attention to units. Let's go back and take a quick look at units. Force of those. What are all our units here? Are units okay? Do we have to do anything? Unit is the force times the distance. What's our force unit? Newtons. Good. That's what a force is in metric, is newtons. What's the distance? Oh, meters, Newton meters. Okay, so our unit is a force times the distance. It's Newton meters. So good, they didn't mess with us. It's nice and straightforward. Okay, great. Now, what's the mnemonic device that allows you to multiply this out? Now, do you have to have a mnemonic device? No. Notice my note sheet, I expanded it out for you. But it can be memorized in this way. You start with this. And let's see. I'm going to go ahead and block it out. You block out that row and that column, and that's kind of your I. And then you do the same determinant I just showed you a minute ago, which is the remaining matrix is a 2 by 2. And so you take this times this, 0.7 times negative 500. You always subtract. And then this times this, which is negative 0.3 times 800. And all together, that's your X coordinate. That's how much rotation there is around the X axis. That's how badly this force is trying to get this pipe to rotate around the X axis. I won't take the trouble to write this down, but I just want to say it really quick. Notice that's the Y distance times the Z force, and this is the Z distance times the Y force. No X's there. So this is kind of cool. Like, you can memorize this from linear algebra. So let's see, 0.7 times, and you got to be really careful with negative signs here because you can totally screw this up. 0.7 times negative 500. Notice it's minus a minus. So I'm going to say plus 0.3 times 800. I got negative 110. And that would actually be Newton meters of desire to rotate around the X axis. So this is just the mnemonic device taken to 3 dimensions. Then you move to J. So this next one is going to be J. And you do the same exact thing. You cross out the row and you cross out the column. And so for J, the matrix you have left is the stuff that's left. So I take 0.5 times negative 500. Always minus. And then 0.3, negative 0.3 times 600. Point 0.5 times negative 500 minus a negative, so plus 0.3 times 600. I got negative 70 Newton meters. Last step, same exact thing. You get to K, which is the rotation around the Z axis. You cross out that row and that column. What's left? 0.5 times 800, always minus 0.7 times 600. Do you see how it's everything times everything? Like those arrows I drew is every possibility up there, at least every diagonal possibility. So 0.5 times 800 minus 0.7 times 600, negative 20. This is almost correct. There's one little thing. Landon, do you know what it is? Sounds like you've heard this before. So you can see the signs are rather confusing to keep track of here. It turns out this first one is always positive. The second one is always negative. The third one is always positive, like it alternates. And so this is actually positive 70. In other words, you switch the sign of the J one every time. Whatever it is, it's the opposite of what you thought. So the moment around O is actually the vector negative 110, 70, negative 20. And it'd be good to say Newton meters after that. Do you notice the answer to that is a vector? Like you didn't get a number this time. You actually got a vector. That's why there's a vector symbol over the top of it. Now, my guess is if you looked in the back and you got it right, you'd say, cool, I got it right, but I don't really understand what I just did. Is that true? Do you understand what that is? What is that? What? I'm lost. What does 110, 70, and negative 20 mean? I don't get it.
It's how badly the whole thing wants to rotate with the force at that position.
Yeah. So it turns out it's telling you really the axis. Actually, let me just show you. Let's go back to the picture. So this point wants to rotate around, but does it make sense to rotate? You have to rotate around an axis. In other words, here's this cup. And if I want to orbit around it, like there's an axis you have to rotate around. Like notice I'm kind of rotating diagonally. Now I'm rotating horizontally. Does it make sense you have to rotate around an axis? If that axis is straight up, then you'd be rotating around it. Watch and see if you can see what I mean. So this says your axis is negative 110 in the x direction. So I'm going to think of that as negative 11. So let's see, I'm going to go that far and call that 11. Did I do that right? No, I didn't. What did I do wrong? What's wrong with what I just did? Come on, time's a wasting. What's wrong? What direction did I just go?
Sorry, I missed what you just did. You went. Oh yeah, that's would be positive x. Should be negative x.
It said negative, so it's actually the other direction. Does that make sense? So it's actually go that way, 110. Then in the y direction, go 70 positive. Which direction is 70 positive? Well, there's positive y, so 70 positive. So I got to go about that far. Does that look up like about, if the first one was 110, does it look like that'd be 70? And then lastly, I go 20. Which direction? Down, negatively. So that'd be not very far. So what that creates is, let's do this in blue. That is your vector. What does that mean? That means that's the axis that this would rotate in if you did this. In other words, it's going to want to go around that axis. That's kind of hard to see. But it's basically saying if you pulled, and you have to think of the pipes as just being the connection to point O. It doesn't matter that they're pipes, and it doesn't matter kind of what angles they take and so forth. It's probably better if you said, forget the pipes. Let's just have this right here. That's the pipe. Forget about the curving. It's like, that's the pipe that goes straight there. And if you pulled in the direction that we said F went in, it would actually cause that to kind of rotate around that axis right there. Now, you don't have to understand this really well, but there's a thing called the right-hand rule. So I'm pointing my thumb in the same direction as M of O. You see that my fingers are curling toward me? That's positive. If you rotate your fingers toward you, that's positive rotation. And that's kind of what I drew. Do you see how I drew the arrow going around, starting up here and going around in that direction? So that's what's considered positive rotation. Would you agree that's what this is causing, is positive rotation? Now, if you decided you wanted to know the magnitude of that, in other words, how many pounds is it? Like in the bike problem, we actually came up with a number for that. If you want to turn it into a magnitude of the rotation, well, then you can just do Pythagorean theorem on it. Wouldn't that be 110 squared? Notice I'm being lazy and leaving the negative signs off, since when I square them, they go away anyway. So 110 squared plus 70 squared plus 20 squared, square rooted, I got 131.9. But do you see how if all you know is the magnitude, that doesn't tell you where it's rotating? Like you got to know what it's rotating around. So the cool thing about this vector answer and why you often just stop right there is not only does that give you the 132 Newton meters of desire to rotate around there, and you can appreciate somebody like grabbing a wrench and trying to turn a nut. You've probably tried that. You hook it on there and you're like, I can't get this thing to go. And so the 132 Newton meters of desire to rotate is actually what's being applied to point O. But what is it trying to rotate around? Do you see what I'm saying? Like you got to know that too. In the case of a nut, I'd be rotating around the axis of the bolt. Does that make sense? So in a sense, that blue MO vector right there is the bolt around which this thing is trying to rotate. So it's kind of cool to be given the moment around O as a vector because it's actually telling you the axis. So this is giving you both the axis and the magnitude, thanks to the form that it's in. If you only have the magnitude, then you've lost the axis around which it wants to rotate. Again, remember, your job as an engineer is to look at this weird system and say, what's gonna happen? What are the forces as a result of this, so that I can make sure it isn't allowed to rotate, if you will. Now, there is one thing that's confusing to me about this picture, and that is, isn't that pipe like screwed into that little flange there? Like if I was to pull on this at angle, the question is really like, will it unscrew? will it unscrew from here? Do you see what I'm saying? Like it's not going to rotate in space. It looks like they've kind of got this thing attached to a wall. So they got all these pipes on here, and then I'm going to walk up to it and like grab the pipe and pull in some direction, if you will. And the pipe's not going to bend. It's not going to spin around inside the wall. The only thing that might happen is it might rotate, you know, in this direction and like get tighter. Or maybe if I sent it in the other direction, it'd be get a little looser. So there's moment around a point, but there's also moment around an axis. Do you see in my notes right below the one that I just referred to? There's magnitude of the moment, and then in bold about an axis. There's how much will it rotate around an axis, and there's also how much will it actually rotate around a point. So as I said, this class, quite understandably, I think, should largely be open note. What I don't want on a test is for you just to copy this example because my test question is so similar. But I do think that it should at least have, you know, a note sheet. And so I'm very interested that when you stare at the note sheet that I gave you, which I'm attempting to pull up now. I'm very interested that this speaks to you. I mean, it speaks to me, but who cares? I already know this stuff. Does it speak to you? I numbered it so that you realize, hey, there's 6 things I need to know for this first test. Notice we're darn close to being done with this first section. 6 things I need to know. The 5th one is moment of a force around a point, employing the cross product. So if I didn't give you this over here, then you'd have to memorize all the stuff I just showed you, which probably with a little practice, you'll have memorized. And if you do take Math 261 next term because of math reasons, which I think you have to take as an engineer, some of you do, you'll be well on your way. You already understand what a determinant is of a 3x3 matrix. So I didn't say any of that language here, but you're taking a determinant of a 3x3 matrix. But I'm just telling you, you know, R cross F, what's R? Rx, Ry, Rz. Those are the Cartesian lengths from O to any point on the force vector, not from the vector to O. Does it make sense? If you went backwards, all the signs would be different. It's from O to any place on the force vector. It could be the arrowhead, because remember the vector slides around, and so it can kind of be anywhere. But in our case, in our problem, the only point we knew was where the vector took off. We only knew the tail. We didn't have a choice. But it's from O to that. It's the distances. So you can't get that backwards. Secondly, what are those forces? What's F? Fx, x, y, z. Those are the Cartesian components of force F. And again, we got lucky this time because it was given to us in that way. So if you memorize what a determinant is, you could get rid of this right here. You don't need that. But of course, that's kind of a big ask, right? So, you know, you could just stare at this and see, but the question is, can you see it happening? How do you get the I component? You take Ry times Fz minus Rz times Fy. Hey, look, that's what I wrote right there. Do you agree that's pretty brilliant? Like for somebody to come up with a way to like write all these numbers in a box in a way that it's like, all you got to do is multiply diagonally and keep track of the signs. It's always minus. And you saw a second ago that the forces were working against each other. I only showed you that once, but one force was trying to get it to rotate one way and one the other. That's why this is always a minus sign, because it's like one is positive, one is negative. Turns out they're always working against each other. That's why one's a positive, one's a negative every single time. So a mathematician, thank you mathematician, said, hey, here's a cool way to think about that. That's a pretty brilliant idea. I'm impressed with people. Humans are smart. Humans doing cool things. As I said, this note sheet is a living document. If you want to argue that there's something else I could put on there that would be helpful to you, if all that smacks of is memorization, even if it's just a note, like I had a little note underneath here, like a little asterisk and says blah, 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 blah. If you find something that you think is helpful, all that is like, what's wrong with that being on there? Do you see the difference between that and me letting you have literally open notes where you just copy an example that looks the same? There is a difference between those two things. You're always going to have your your cheat sheet in front of you as an engineer, but every time you come to a new problem, you're going to have to figure it out from scratch. You've got to learn how to think as an engineer, but you don't have to memorize formulas. You can look those up. Every engineer has a book with formulas next to them, and it'll have things like what I shared here. How's your brain? You tracking? Is this hurting you? Speak up.
Well, I did have a question about, so you said that the distance to any point along that line of the force vector,
Yeah.
we can use that.
Yeah, isn't that
Even
weird?
though those will all be different distances.
Yeah. But the problem
Okay.
is when you change, say, the X, the Y is going to change with it. And so the net result is the same. Now that should bother you. Like me
Yeah,
just
that's-
saying that and that being true, two different things. Like what? There's no way that's true.
Yeah, maybe
Um,
that's why that's confusing. Is in physics, I only remember doing it to the point of the actual force vector where it took off.
mhm.
Work. So maybe I
Well,
don't know the difference between.
That's an easier way to visualize it. But the thing I showed you before, that if the vector is pointing this way, that its line of action extends everywhere in both directions. And so you can think of it, you can't move it down here, but you can move it
Yeah.
any way you want. So see, if here's the tail and I move the head to there, well, now all of a sudden it's in the same location. So you see what I'm saying? It's kind of like, where is this vector? Well, it's everywhere on this line. That's the simple logic as to why that is. And I will tell you, that did not make sense to me the first time I taught this course, Ben. I was like, what? There's no way that's true. I had to play around with it a bunch and so forth. I mean, I'm obviously, the book and I am not going to tell you something that's not true, but I'd encourage you to play with that. Let's see, 1209. So here's an example, Ben, of where you could do this two different ways. Now again, so here's this trap door, and I kind of like this problem because it sort of feels real. Like here's this door that's like a trap door down into a room down below, and you basically say, hey, I think I'll open that door up. And so there's a chain hooked to it, and so you pull on the chain, and I can pull in the chain in any direction I want. But notice, because of the hinges, does it make sense it's going to rotate around the axis AB? If you pull on it, that's what it's going to do. It's going to rotate around an axis. It's not going to rotate around a point. However, can you appreciate that although it will rotate around axis AB and the door will swing open, one hinge is probably going to have more force on it than the other one? Do you understand that? And so if the chain was pulled in a certain way all the time, like a drawbridge, and you're going to lift this thing up, and so it's always going to rotate around the axis at the bottom, one hinge might get more force on it. And if it does, you might have to have more screws down there. So let's quickly, before we run out of time, see if we can set this one up. Notice it says, determine the moment of the force F about the door hinge at A. They did not say around axis AB. This is the same problem we just did. So it's find the moment of the force F about point A. They said hinge A, not point A. It's the same problem we just did. I just want to know, if I give you a couple of minutes, can you set up the determinant for this? Notice they did not give you the forces this time. Bummer. They told you the force F is 80. They did not give you the components of that force. You got to figure that out yourself now based on all the dimensions that are in this shape. So start with that. Force is 80 pounds, but I need force of X, force of Y, force of Z. Can you still do this from chapter 2? If all you did was memorize chapter 2, you're probably already beginning to forget it, and this feels really hard. It's pretty hard. It takes a lot of practice. I'm going to give you enough time to try to answer these 3, and then I'm going to answer them. If you get done ahead of me, then go ahead and try to move on. But Just remember, you can only move in X, Y, and Z directions. So let me interrupt for a second and say this. If this force starts from that tail of the vector and aims toward D, that's the only information I have about where this thing is actually going. So how do I get from C to D? Well, I go, I guess, down in Z. Notice I just went parallel to Z. Could I go X first? Yeah, there's other ways you can get here. But the point is you got to go X, Y, and Z in whatever order you want to. I'm just seeing if I went that way in X and I went this way in Y. So if I went negative Z and if I went positive Y and then negative X, that would get me there. That's one way to get there. Maybe that's not the only way, but that's one way. So I need to know what all those links are because it's those links that give me the proportions that are going in each one. It's the proportions, the same proportions for these links match the proportions for the forces. The total force is 80, but what are the links? Well, there's only one that I see. That negative X is clearly 5. That was easy. But notice Z and Y, I'm going to have to work for. Did you see that? So I see over here on the far side of the door that door is 4 feet long, which means over here it'd also be 4 feet long. And so I have this right triangle there where this angle is 45, that's 4, and there's kind of my negative Z. And then there's a chunk of that Y right there, not the whole Y. Part of the Y is 3, but then I need that little chunk right there. So I'm just going to say question mark. So I could say the sine of 45 is opposite kind of that negative Z number. I don't want to call it negative Z anymore. It seems kind of confusing. So I'm going to call it A for now. Sine of 45 would be A over 4. Oh, okay, that's easy. 4 times the sine of 45. 4 times the sine of 45 is 2.8. I don't know how to round. I'll call it 2.83 for now. So A is 2.83. And because this is a 45 triangle, that means the other one's also going to be 2.83. So that saved me some trouble. That was awesome. So watch this. Do you understand this? This is kind of a cool way to write this down. If I said vector CD and put a vector sign over the top of it, I could say in the X direction, that's -5. In the Y direction, it's 2.83 plus 3 more. So that'd be 5.83. That's positive. And in the Z direction, I was down 2.83. Like that's kind of a cool way to write that down. Those are lengths. And maybe I should come back here and say, by the way, that's in feet. Those are the lengths. That's how far it is from C to D if you only follow the coordinate axes. I'm very interested that this go into you deeply and not be just something you have to memorize. So what does this have to do with anything? Well, it's proportions. I also need then the magnitude of CD, which is Pythagorean theorem. So if I take 5 squared plus 5.83 squared plus 2.83 squared and square root them, I get approximately 8.19. So somebody tell us, like, why did I do all this? This seems to have nothing to do with the problem. Remember, I'm trying to get forces of X, forces of Y, forces of Z. And again, I'm interested in you conceptually going, oh yeah, that makes sense why that would work. As opposed to just following steps. Why did I do all this? What am I going to do with it?
Well, we need to use it to find the direction that F is going in.
Yeah, that tells me the direction F is going in. Now I can see that.
Yeah, I think we'll need to make a unit vector out of this CD so we can just get the direction and then multiply that by the magnitude of the force.
Yeah, the key is the proportion, if you want to understand this logically, the proportion of this 80 in X is going to be 5 over 8.19. The hypotenuse is 8.19, but the portion of that is in X is 5. So if I just take negative 5 over 8.19 and I multiply it by 80, then that'll tell me what proportion of 80 is devoted to the X direction. And the negative sign counts. I get roughly 48.8. I get negative 48.8. It tells me the amount, which is roughly 49, but more importantly, it tells me the direction. Oh, it's negative. So this is the only one I'm going to write in the picture, but does it make sense? You're essentially getting that force right there. That's what the 48.8 pounds represents. So then I'm going to do the same thing with all the other ones. And so because Y was positive, that's its proportion is 5.83 over 8.19, also multiplied by 80. And if you do read the book, which I hope you do, what Ben said about a unit vector, that's what this is really doing, is changing CD into a unit vector. If I rewrote every one of those numbers as over 8.19, then it would make a unit vector, meaning if I did the Pythagorean theorem on it, I'd get 1. What that does is cleanse these lengths of a size. I want to multiply it by something that is sizeless. The unit vector CD is just all of those amounts divided by 8.19. And the magnitude of that is 1, which means if I multiply by 80, I'm not going to be screwing up the 80. I'm only going to be parsing it out into the chunks, the proportions of 80 that go in each direction. So I got 56.9 pounds for this one. And lastly, the force in the Z direction is negative 2.83 times 80. I got 27.6, and I'm not rounding good. This is not good. If I call 27.64 27.6, then I'm going to probably get the final answer, according to the back of the book, a little wrong. So I'm just being lazy. So there's see how much work that was? Like last problem was just given to us. Wow. We had to figure it out ourselves this time. Nasty. Second thing, how far is it from A, the distance from the point, from A to the force vector? Do you agree you have two choices here? because I know where the vector started and I know where it's going. I know that it ends at D. How far is it from A to D? So I have two choices. One is how far is it from A to D, or how far is it from A to C? So I said in my note sheet, any distance from A to the vector, any place you know where that vector is. In this case, I know where the head and the tail is. So it looks like A to D is really easy, because from A to D, I'd go 1.5 positively in the X, and then this far positively in the Y, and that was that 3 over there. How far in the Z? Nothing. I didn't have to go up or down at all. So there's your R vector. From A to C is tougher. If you want to, I'll leave you to try this with the distance from A to C, which I think because of the calculations we just did, at least I could write down. Let's see, if I went from A to C, how far is it from A back to this point right here? Well, that's 1.5 and 5. So isn't that distance to right there positive 6.5? You agree with that? And then then from there, I'm going to take off in this direction. That's negative Y. And we figured out a minute ago that was negative 2.83. So that'd be negative 2.83. And then lastly, I go up that Z right there. Remember, it's from A to C. I go up that Z, so that'd be positive 2.83. What my note sheet said is whichever one of those you want to use for R, for your R distances, they'll give you the same answer. Obviously, the AD one looks simpler, but I would encourage you to try it with AC and see if that I'm actually telling you the truth. And so now I have all the ingredients I need, and I'm going to stop with this because I'm running us out of time. But if I want to know the moment and get in the habit of labeling this stuff good, the moment around A as a vector, put a little arrow over the top of it. That's R cross F. And we said that that is written like this. To keep track of the X, Y, and Z component, we write down I, J, and K. And the first thing we list is R cross F. So the R's go first and the F's go second. So my R's were all positive. I'm going to use 1.5, 3, and 0. That should save me some time since one of them is 0. And my force vectors are negative 48.8 in the X, 56.9 in the Y, and 27.6 in the Z. And now if I can take the determinant of that, and you may remember this problem said, express the result as a Cartesian vector. In other words, they're not making me convert this into coordinate direction angles and magnitudes. They're just saying you just get to leave the answer as a vector and you're done. Thank you for that, is what I'm saying. To help you with this, I'm gonna do this kind of quickly. So, but I at least want to write this down. So I'm going to cross out the I row. So that leaves for my I, I'm going to write the I in front this time. That leaves 3 times 27.6 minus 0 times 56.9. Yeah, that's going to save me some time. And then when you get to the J, remember it was always negative. So I'm going to write that negative sign right there. So the J is cross out the J row. So that's going to be, again, multiplying diagonally, 1.5 times 27.6 minus, hey, good, 0 again, 0 times 48.8. And then it's plus, so it's plus I minus J plus K. What's the K row? Last one to cross out. I need a light color. Pink, I guess. Cross out the K row. what does that leave? 1.5 times 56.9 diagonally from upper left to lower right minus 3 times negative 48.8. If I can type all that and not screw it up, I have my answer. And again, the answer is a vector. So moment around A, desire to rotate around A is this vector. So I'm going to write it without I's, J's, and K's. I'm going to write it in vector form. So all I have to do is go 3 times 27.6 minus nothing, and I get 82.8. Second one, I have the same thing. I go 1.5 times 27.6 minus 0 times something. I get a positive, but remember there was a negative out in front of this, so that's actually going to go down as a negative number. And then finally, I've got a lot to do. 1.5 times 56.9 minus 3 times negative 48.8. I got positive 231.75. What are the units of that? You can't leave that off. What was I multiplying? My radiuses were in feet. And my forces were in pounds, and I was always multiplying feet times pounds. So this is foot-pounds. You need that answer. So again, I just did math for 30 minutes there. The chances I didn't push one number into my calculator wrong, or write something down wrong, or lose a negative sign, or I can't read my handwriting and I lost a decimal point. I am not overly confident I didn't make a math mistake here. So easy to do. I'm going to see if I did this last year and see if I got the same answer. Yeah, I did. I got the same answer I got last time I did this. Of course, in the back of the book, though, the last number would not be 231.75. It'd be 232, right? 3 significant digits. And because I rounded too early, if I looked in the back of the book, I wouldn't be surprised if this said 82.7 or 82.6. Again, I do not want you to redo your work as a result of that. It'd be better if you just got in the habit of an engineer of carrying your decimals out further the whole way. But I now know how badly that 80-pound pull that I pulled in the direction that I pulled, I know how badly it's sort of torquing on that hinge over there. And you can't appreciate in this picture probably that over time, those hinges are going to get kind of weak. And so that does want to rip around that A hinge. Fortunately, B is there resisting it, right? B is not going to let that happen. The B hinge isn't going to let that happen. I'm going to quickly draw this and then I'll shut up because I know we're way over time. But notice, where is this vector pointing? Remember, this vector is the axis around which this wants it to rotate. 82 in the X, negative 41 in the Y, 232 in the Z. So let's see. I'm just going to make up some rough numbers here. I'm going to erase this, but if this was 1, then this is double that length. And 4 goes into 24 about 6 times. This would be like 6 times the length. So if the first one is however long it is, I want to make the second one double and the third one kind of triple that. So just trying to make a rough drawing. So first 2 in the X direction and then negative 1 in the Y direction. Just want to see if I can picture this. What's going on here? So 2 in the X direction. That was positive. Negative 41 in the Y. So that'd be going that direction about half as far. And then about 6 times that in the positive Z direction. So what you need to understand then is, what did we just find? We just found that right there is literally the magnitude of around A as a vector. Can you appreciate, can you see it? If you pulled on this chain at the angle that they're describing, that the door would want to rotate around that axis right there? Again, I find that hard to visualize, but that's the meaning of the magnitude of A that we just got here. That's the axis around which it wants to rotate. Right-hand rule, thumb goes toward the arrow. That means it wants to rotate according to my fingers, kind of toward me. So that means it's wanting to rotate in that direction. That's positive rotation. And you can see from the chain that that's exactly what it would cause, is rotation in that direction. Whew. So a lot to think about.
Actually, I did it with the other point, and I got the same answer, except for X and Y were like flipped signs. I don't know what happened with that. I must have done something wrong there, but the numbers are the same, which is
Cool. Let's make sure I wrote it down wrong, or I didn't write it down wrong. X is positive.
That
Y
might
is
make
negative. No, that's right. I got it right.
Yeah, must have done something with my signs.
Yeah, you should get exactly the same thing. But this business of the fact that the I is always positive and the J, you have to change the sign. And a lot of times you're subtracting a number times a negative, and man, it's like so easy to make a mistake with this stuff. I got really lucky in this problem the way I did it because I was always subtracting 0. Oops. I was always subtracting 0. So, but when this says like a negative number minus a negative number, and then you're changing the sign to a negative, it is so easy to lose one of those signs. Try to work clearly, because on a test, if I can see that you had it written out correctly, but punched it into your calculator wrong or something, it's very hard to get the question like this right. You can appreciate that even if you know what you're doing, it's sort of a miracle if you don't make some kind of a silly mistake. But I would encourage you to pore over and notice what we did. As far as the syllabus is concerned, we covered 4.4 and 4.5. We still have chapter 4 to do, other things in chapter 4 to do. But I've assigned, 10 questions now that you should be able to do, but that certainly does not mean sit there watching TV while you're on the phone and be able to do it. Like, you're probably gonna have to close all the doors and windows and like focus. And this is hard. This is a challenge, but it's a huge part of what you do as an engineer, just understanding rotation. And the real world is 3D, so can't really avoid that. All right, get yourself out of here. Go recoup, go work on this. Send me a text this weekend if you'd like to discuss some of the homework questions, because again, ideally, you're going to give me your homework Monday so that we can start on the things that are next on Tuesday.
All right, thank you.
Actually, before you go, Ben, I'm actually looking at my notes right now, and my notes actually say this one is negative and this one is positive, which means I made a mistake.
So there is actually, if you're gonna go up all the way, and there's force of Z.
Yes. Yeah, what's wrong with that?
Negative, it should be negative.
It should be negative. I lost that negative sign. So what ramifications does that have? By the way, I didn't say this out loud, but I was looking at the picture I drew and I thought that does not look like it would be rotating around that axis. That was bothering me. So that 27, every place that 27 shows up should be negative, and of course it only shows up in the matrix. And so that should have been negative right there, which means it should have been negative right here and negative right there. So that would make this number negative. And then here, because this is a negative times a negative now, it would mean that's a positive. So you were right, Ben, I was wrong. I do want to quickly go redraw this picture. So it's now it's negative x, because maybe this won't bother me so much.
Which is weird because it seemed like it made sense in that other direction, but I guess.
Well,
maybe-
the problem is that that chain should be perpendicular to the axis. Does that make sense?
Oh,
And that
yeah,
did
that
not
was-
look perpendicular to me. That's
Oh.
what was bugging me.
Yeah.
So negative x, positive y. So that means I'm going this direction, negative, and then positive y, and then positive z. And so that is our moment vector. There we go. Does that look perpendicular to the chain now?
Yeah, it does.
So again, as a teacher, I'm glad when stuff like that happens. I mean, I just sat there telling you how easy it is to make a sign mistake. And not only that, I looked at my answers from before, and because the numbers were correct, I thought, oh, I must have got it right. But now that actually looks perpendicular to the chain. And so again, I have the axis around which that rotates, and the length of that vector is actually the magnitude of the rotation. So that's kind of cool. Sorry about that. Stuff is hard enough if you don't. But the other part of this is, I mean, you're the only one left, Ben, but you know, if I'm grading your test, am I going to be able to read your work enough to be able to see you lost that negative sign? Because in my case, what I would have done is came back and said, dude, you know, look at that negative sign you lost. And then I would follow it through and realize, yeah, actually everything you did was right. If you had not had that, then these would have been correct. And, you know, then I can take off very few points. Although in the real world, the bridge fell down and you got fired. Like it doesn't really matter what
Give
the
me that a second.
reasons were, but
Yeah. All right.
good. All right.
Thank you.
Thanks for coming. I'll see you